Howdy, today on Flipping Science we're looking at reaction rates. So today we're going to focus on this one down here. So you need to be able to draw and interpret graphs representing changes in quantities or concentration of reactants or products against time. So we've got to be looking at how rate changes over time in a chemical reaction. So chemical reactions take place at a variety of speeds. Precipitation reactions, they can be quite quick. Organic preparations, for example making an ester, that can take half an hour to an hour. Rusting an iron, that can take place over years. So for industry, it's important to know how quickly reactions occur and how to change the speed of reaction. In industry, you want to make as much product as possible in the shortest amount of time. That will give you more product to sell quicker. But if you speed up a reaction too fast, you might get something bad happen. So an example of when things go badly is the Bhopal disaster. So outside of Bhopal in India, there's a pesticide factory. One of the chemicals they used was methyl isocyanate. They had some water storage tanks where they stored the precursor. There was a water leak into those tanks that led to an increase in the reaction rate, producing the methyl isocyanate gas. All the safety systems that were in place to stop the gas escaping in the case of a overpressure didn't work, and a big cloud of gas was produced. It wandered over the city, followed the wind patterns, and killed thousands of people. So in this case, the failure to control the reaction rate of the exothermic reaction occurring led to the disaster happening. So how fast or slow a reaction takes is called rate of a reaction. And like any rate, it's how much you're doing of something over a certain period of time. So a rate is a measure of how much you change maybe a reactant or a product concentration over a period of time. Just the chemical equation doesn't tell you how fast a reaction is, so the way we do this is we run the chemical reactions and we figure out how much reactant is used up per unit time, or how much product is produced per unit time. And that way we can figure out how quickly or slowly the reaction is. So here's an example reaction that we'll look at. So you have a strip of magnesium, you chuck it in some hydrochloric acid. Initially, as soon as you shove the magnesium in the hydrochloric acid, you get a lot of bubbles. Over time, the number of bubbles starts to decrease until eventually the bubbles stop. Bubbles can stop for a few reasons. You might have run out of magnesium ribbon, which is what is happening in the picture down here, or you might have run out of acid, so there's no more acid to dissolve away the magnesium. So initially lots of bubbles, over time the bubbles decrease, and then eventually there's no bubbles left. So here's the equation for the reaction. So magnesium plus hydrogen ions goes to magnesium ions plus hydrogen gas. Magnesium and hydrogen ions are being used up, magnesium ions and hydrogen gas is being produced. So we could measure the rate of this reaction in many ways. We could look at how much magnesium is being used up per unit time, but that would be difficult. We could look at the amount of hydrogen ions being used per unit time. We could do that using a pH probe, for example. The amount of magnesium ions being produced, again, that's a little bit difficult. Or we could measure the amount of hydrogen gas that's being produced. We could measure the volume of hydrogen gas, or we could measure the change in mass of the magnesium and acid mix, because as the hydrogen gas is produced, the hydrogen gas leaves. So we get a loss of mass over time. So there's many ways that we could measure the reaction rate of this reaction. So here's a picture showing some ways. So like I said, we could have our beaker with our acid on a balance. We chuck in the magnesium and we watch what happens to the balance mass on the balance over time. So as the hydrogen is being produced, the gases of hydrogen escape, and that leads to a loss of mass of the reaction mix. Another way we could do it is this way. So we've got the magnesium and acid in a beaker. We put a burette over the top. And as the hydrogen gas is being produced, it bubbles up through the funnel into the burette. It displaces any of the water or air in the burette, and the volume changes. And we could monitor the change in volume to figure out the rate. So here's some experimental results. So we've got time, we've got volume of hydrogen. As the time goes on, the volume of hydrogen is being increased until we get to this point here, where the volume of hydrogen being produced drops down to zero. So the volume of hydrogen doesn't change over time. So what we'll do is we'll graph that, and we'll have a look at what the graph shows us. So here's our graph over here. So we can see that initially we're getting a large amount of hydrogen being produced, but as time goes on, the amount of hydrogen being produced per minute, or per time interval I should say, is starting to drop down. If it was the same all the way, we'd just have a straight line going on forever. But instead what we get is initially a high rate, and the way that we measure rate is really just by looking at how steep the curve is. So in this case it's steeper at the start, and then as time goes on it gets to shallow, and then eventually it completely shallows out and we're not getting any change in volume. So that's what we're seeing over here. So initially we have a very steep curve. As time goes on, the steepness decreases until eventually it becomes horizontal. So why do we get a curve like that? Well, it all boils down to something called collision theory. Collision theory is talking about how you make products from reactants. So if you want to make a product, you need to have your reactants colliding with enough speed, which is energy, and in the right orientation, facing the right way, and then you'll get your products being produced. So let's have a look at an example down here with hydrogen and oxygen. So here we have hydrogen and oxygen. We want to make water. To do that, we need to collide the hydrogen with the oxygen at enough speed to break the bonds between the hydrogen atoms and the oxygen atoms over here. If they don't collide with enough speed, they won't break the bonds and we won't be forming this activated complex. So the hydrogen and oxygen, they need to collide together with enough speed to break the bonds that join them together. When they do that, we get an unstable complex being produced, and that's where we form new bonds between the oxygen and the hydrogen. And then that leads to the production of water. So we call this a successful collision when the particles collide with the right energy and in the right orientation. So initially, when you have a reaction mix, you've got a large amount of reactants together. So if there's a large amount of reactants, then they're going to successfully collide together because the probability of a reactant colliding with the other reactant is quite high. As time goes on, however, so we're following the green line on the curve here, as time goes on, there's less and less reactant available because you've made product. And since there's less reactant, you're going to get less successful collisions, so that means the rate of production of product is going to decrease. And again, as time goes on, there's less and less reactants until eventually you get to the point where you don't have any reactants left, or you've run out of one reactant, and that means you're not going to be making any product anymore, and that means your rate isn't changing. So initially you have high concentrations, which means there's successful collisions, lots and lots of successful collisions. As time goes on, there's less reactants available, so there's going to be less successful collisions until eventually you run out of a reactant, or both reactants, and that means the rate of production decreases to zero because you're not making any product anymore. So here's a question. It says, in the absence of sunlight and at a low concentration of nitrogen dioxide, ozone is removed from the atmosphere shown by this reaction. In a laboratory investigation, concentration of ozone was measured over a period of time, as shown in this graph. The question says, using collision theory, explain why the concentration of ozone fell more rapidly in the first 3-minute interval than in the interval between 3 and 6 minutes. So if we look at this in the first 3 minutes here, that means we've got a lot of reactant particles, in this case the nitric oxide and the ozone, but a lot of them together, and they'll be colliding with each other, and there's lots of them, so the frequency of successful collisions is going to be quite high. In the second 3 minutes section, so from 3 to 6 minutes, there's less and less nitric oxide and ozone available because you've produced nitrogen dioxide and oxygen. So we've reduced the amount of reactants, which means there's less of them able to collide with each other, and that's going to reduce the reaction rate. Because you have fewer particles of the right type that will be able to collide with each other, there's going to be less successful collisions over time. So today in Flipping Science, we looked at what the rate of reaction is and how it changes over time. That's it for Flipping Science today. See ya.